Hello, good afternoon to everybody. Thanks for showing up for this second section, the first section for this afternoon. This section is called the Aerial and Aquatical Vehicles. I am Paulo Rosa from IME, and I think I just can call the first presenter, the first presenter, that is Lídia Rocha, with the topic Analysis and Contributions of Classical Techniques for Path Planning. Is it all right, Bruno, to play the video?
Hello, I present the work named as Analysis and Contributions of Classical Techniques for Path Planning, developed by me, Lídia Rocha, and Kelly Foldini in the Federal University of São Carlos. The presentation will follow this order. Firstly, I will present a brief introduction, use the approaches and detail the preliminaries to do this work. Finally, show the simulations and explain the analysis, followed by conclusions and future works. Unnamed air vehicles, or UAVs, are used for professional and recreational purposes in several tasks. Professional goals will use autonomous flights. For it, it's necessary to use path planning tasks to UAV move between two nodes without collisions. Actually, there are several path planning techniques. Among them, the classical techniques have the greatest reliability and can be classified into exact and approximate. The main exact classical approaches are a star and associated potential field. These tags always return the same path because they are based on mathematical equations. Besides that, they are highly accurate. And the main approximate classical approaches are probabilistic roadmap, rapid explorer random tree, and rapid explorer random tree connected. These tags are based on random nodes that can generate an appropriate trajectory having low computational costs. The star algorithm was developed to improve the computational cost and execution time in search problems of the graphs. The algorithm is based on the use of a heuristic defined to guide the search process. This heuristic estimates the cost traveled from the start to the goal node, aiming the short distance. The artificial potential field algorithm makes an analogy to electric fields, creates a map in which the UAV is inserted based on the electric field. The method considers the UAV as a particle that is influenced by the local field. The map is a potential field formed by the attraction force of the goal node and the repulsion force of the obstacles. The probabilistic roadmap takes random samples from the environment, tests them for whether they are in the environment, and connects them. This algorithm consists of two separate phases. The first phase is learning and the second phase is acquiring. In the first phase, the UAV creates a knowledge about the region to be explored in a probabilistic roadmap of the environment. Moreover, in the second phase, the map is used to find the shortest path between start and goal node, generating the trajectory. The RT algorithm tends to search for solutions in larger environments with obstacles. This algorithm increases the tree from the start node to the goal node, avoiding the obstacles. The main advantages of RT are the expansion, that is heavily biased towards unexplored portions of the environment, the distribution of values in an RT approach the sampling distribution, leading to consistent behavior, and RT always remain connected, even though their number of edges is minimal. Several techniques were created intended to improve RT performance. One of them is RT Connect that uses two RT, one starting at the start node and the other at the goal node. This method divides the computational codes in half, improving the technique. The simulation uses three environments. The first is a 2D indoor environment with 100 square meters, the second is a forest with 40 square meters, and the last is a 3D indoor environment with 20 square meters with 5 meters of height. 2D simulations were realized 50 times to obtain the statistical analysis of each algorithm, and the 3D simulation was realized 1 time to understand the behavior. All simulations were done in known environments in Gazebo Simulator with multi-robot system in Python 2.7. We used the UAV F450 with MC control communication trophy ROS. The parameters considered in each algorithm are shown in this table. Algorithms use robot radius as 40 cm and path resolution as 0.1%. APF has a recursive computational gain is 0.8, the attractive potential gain is 1, and the max number of iterations is 1000. The purpose for the map uses 200 samples, 15 edges, and an expansion distance of 20 meters. In RT and the RT Connect, the sample rate is 5%, expansion distance is 5 meters, and the max number of iterations is 5000. The figure shows the best trajectory in 2D environments of each algorithm in Simulator Gazebo. All the algorithms generate good trajectories. The star, APF, and PRM carry out as few curves as possible. Furthermore, the PRM, RT, and the RT Connect.
I'm sorry. Good afternoon, everyone. I believe you're saying the presentation is frozen.
Yes, yeah. But I think it's frozen.
Okay, the problem is I can't see where exactly it is frozen, so I can go back.
It is in the third slide.
Slide number 3, correct?
Slide number 3, yes.
Okay, so let me see what I can do. Okay, I'm gonna stop sharing my screen, share it again, and then put the video in the beginning of slide 3.
I think you can put on the beginning of slide 4 because it's
okay.
Okay.
Just a second.
The STAR algorithm was developed to improve the computational cost and execution time in search problems of the graphs. The algorithm is based on the use of a heuristic defined to guide the search process. This heuristic estimates the cost traveled from the start to the goal node, aiming the short distance. The artificial potential field algorithm makes an analogy to electrical fields, creating a map in which the UV is inserted based on the electrical field. The method considers the UAV as a particle that is influenced by the local field. The map is a potential field formed by the attraction force of the goal node and the repulsion force of the obstacles. The progress roadmap takes random samples from the environment, tests them for whether they are in the environment, and connects them. This algorithm consists of 2 separate phases. The first phase is learning and the second phase is a query. In the first phase, the UAV creates a knowledge about the region to be explored in a progress roadmap of the environment. Moreover, in the second phase, the map is used to find the shortest path between start and goal node, generating the trajectory. The RT algorithm tends to search for solutions in larger environments with obstacles. This algorithm creates the tree from the start node to the goal node, avoiding the obstacles. The main advantages of RIT are the expansion, that is heavily biased towards unexplored portions of the environment, the distribution of variables in an RIT approach the sampling distribution, leading to consistent behavior, and RIT always remain connected, even though their number of edges is minimal. Several techniques were created intended to improve RIT performance. One of them is RIT Connect that uses two RIT, one starting at the start node and the other at the go node. This method divides the computational codes in half, improving the technique. The simulation uses three environments. The first is a 2D indoor environment with 100 square meters, the second is a forest with 40 square meters, and the last is a 3D indoor environment with 20 square meters with 5 meters of height. 2D simulations were realized 50 times to obtain the statistical analysis of each algorithm, and the 3D simulation was realized 1 time to understand the behavior. All simulations were done in known environments in Gazebo Simulator with multi-robot system in Python 2.7. We used the UAV F450 with MPC control communication trophy ROS. The programs considered in each algorithm are shown in this table. Algorithms use robot radius as 40 cm and path resolution as 0.1%. APF has a repulsive computational gain is 0.8, the attractive potential gain is 1, and the max number of iterations is 1000. The purpose for the map uses 200 samples, 15 edges, and an expansion distance of 20 meters. In RIT and RIT Connect, the sample rate is 5%, expansion distance is 5 meters, and the max number of iterations is 5000. The figure shows the best trajectory in 2D environments of each algorithm in Simulator Gazebo. All the algorithms generate good trajectories. The star, APF, and PRM carry out as few curves as possible. Furthermore, the PRM, RIT, and the RIT Connect smooth the turns as much as possible. According to this table, the RIT Connect returns to the trajectory in less time, and the A-star returns the shortest path. Although the RIT didn't return in the shortest time, it was close to the lowest, and returned the trajectory shorter than the RIT Connect. The memory and CPU of all tags are similar. Even so, RIT was the one that used the least CPU. This figure shows the simulation in the forest. In this case, there was no trajectory of APF, because the algorithm couldn't reach the goal node, as the APF tends to fall in a local minimum when the obstacles are symmetrical. The star and PRM made trajectory with the least turns possible to complete the mission, and the alt algorithms smoothed their curves, being good paths to be followed by the UAV. The RIT made an unnecessary curve at the end of the trajectory. Still, since it's smoothed, it only increased the path length without impairing the UAV's movements. In this scenario, RIT returned its trajectory in a shorter time, followed by RIT Connect. The shortest trajectory was that of A-star, followed by RIT. The memory and CPU used by each algorithm don't vary much. Nevertheless, it's worth mentioning that A-star used the most significant memory and the lowest CPU usage. The algorithm isn't complex, but it's necessary to save much information to perform it. It is why it's needed to examine all the nodes in that scenario. The figure shows the simulation with A-star, RIT, and the RIT connecting a 3D scenario in the gazebo. These techniques were chosen because they present the best performance. In all scenarios, A-star returned the shortest path among all the techniques. Moreover, the RIT and the RIT Connect had a low execution time, and the RIT, besides having a low execution time, also had a short trajectory. In this scenario, A-star presents the best trajectory for having accomplished the least number of curves possible. On the other hand, despite the RIT path always going towards the goal, it made many unnecessary curves. Furthermore, the RIT Connect turns to the opposite side of the goal node, only increase the trajectory. However, all paths are smoothed, and the UAV would have no problem completing them. In the simulation, the tanks with the shortest times also showed the short trajectories. That is, A-star presents the best results, followed by RIT Connect, and finally RIT. The memory and CPU usage of A-star and the RIT are similar, while the RIT Connect uses more computational power than A-star and RIT. With that simulation, it's possible to perceive that for 2D environments, the RIT and the RIT Connect return trajectory faster. However, in a 3D environment, the algorithm has more difficulties finds the route since it's more possible routes and more computational power. As the A-star presents the best results among the tanks, a robustness analysis is made between the path planner and the path followed by the UAV in gazebo using A-star algorithm. The path plan generates the blue path and the red path that the UAV follows. Although the difference the X and Y axis is minimal, the most significant difference was present in the Z axis. In this way, we realized that the UAV can use the trajectory generated by the path planner, because the difference in Z axis was not so significant to cause collisions, and the tiny difference in Z and Y axis shows how good the trajectory is to be used in real UAVs. The path length suggested by the algorithm is 57.43 meters, and the path followed by the UAV is 67.56 meters. In this paper, we compare a classical approach to understand the advantage and disadvantages of it in different environments, aiming to help other researchers to choose the best algorithm. Our algorithm shows good trajectories to be followed by the UAV, because they have a few curves with well-smoothed paths. However, the tags A-star, RET, and the RET Connect present the best results concerning the algorithm's execution time and the path length. The A-star returns path with few curves, having good results in missions where it's necessary to increase speeds, such as delivery and agriculture. The RET presented the territory with more curves and have good use in dense environments, such as forests. Besides, the RET Connect showed the path that tends to explore more of the environment, having good use in missions such as search and rescue. In future works, we plan to carry out the tests in a real environment and develop a benchmark framework with these techniques. These are some references used. Thanks to everyone for listening. For more information, this is my contact.
Thank you, Lydia. Congratulations for the research and the presentation. And we have a time for one question. Is there any comments? Any question for Lydia? Also, I have a question for you, Lydia, and it's just because you at the first time you said that you would make a comparison between 5 methods that in the literature it was chosen to be the best path planning algorithm, such as the A-star, APF, PRM, RTT, and RTT Connect. And you used the results of these references to try to do your research in order to find the best path planning trajectories, algorithms, based on such parameters as faster, less computational time, real-time 2D, DD, 2D, 3D, indoors and outdoors environment. But the question is, in the reference, how they find that these 5 methods were the best performance methods?
Okay, firstly, thanks so much, Paulo. In this work, we analyze the classical techniques. Between them, the classical techniques is divided into exact and approximated. Exact techniques have several techniques as A-star, voxels, grids, and among all techniques. Between them, A-star is the most used technique because they are simplest, and the difference in A-star and the other techniques is not so much. It's more because of them is based in grid, so the complexity time is so very similar. So we prefer to use A-star to be more faster than the other techniques and for being more useful between the researchers too, and have more options than literature to future improves, such as R-star, E-star, B-A-star too. So will be facilitated to be improving. And in approximate techniques, there are two options, the main two options in the case, PRM and RT. But RT have so many options as RT, RT star, RT connect, RT AC, RT AC star. I have a lot of options. So we got the main of the tags. In other words, the full tags of them to understand how it works and to improve according the necessary of the work. But we choose the RT Connect because we read a paper that show how bidirectional tags can improve the computational costs. Decreasing the computational, decreasing the time to find a path.
Okay, thank you very much for your explanations, and I hope you can in the future do some real experience with your results, simulated results. Thank you very much. So we are going to the next presentation.
Thanks so much.
Thank you, Lydia. You're welcome. And the next presentation will be from Matheus Araújo, Cooperative Observation of Malicious Targets in a 3D urban traffic environment using UAV. Okay, Matheus Araújo.
Sir, I'm here. Hello, my name is Matheus Araújo from the graduate program in Computer Science at the State University of Ceará, which is located in the city of Fortaleza in Brazil. I will present the work entitled Cooperative Observation of Malicious Targets in a 3D urban traffic environment using UAVs. Introduction. The cooperative multi-robot observation of multi-moving targets CMOMMT considers two kinds of robots, the observers and the targets, in a 2D field environment partially observable. Cooperative Target Observation (CTO) considers that the environment is fully observable and that the targets cooperate with the observers informing the locations. The observer's task is to search and observe the target robots on a radial limited sensor range, minimizing the total time in which targets escape from the observation of the team of observers. Recently, we improved the approach based on K-means and introduced the notion of an organization in the team of observers. CMO, MMT, CTO are the core of many problems in real-world situations. In many of the approaches to these problems, the focus was on the rationality of the observer's agent movement. In our recent approach, we try to improve the rationality of the target agents with a semi-neural network incorporated in each independent target to predict and avoid the observer's movement. This work proposes an approach to the extended CTO problem. We call the CTO Urban 3D problem, a simplified urban traffic scenario in 3 dimensions for the CTO, considering that suspect transport like cars or buses are targets and UAVs are observer agents. The approach employs genetic algorithms and recurrent deep neural networks to improve the performance of target robots and observer organizational behavior hierarchical consolidated in the CTO literature for UAVs observers robots. To evaluate the proposed approach in agent-based simulation, we will measure the average number of target evasion and subtracting the total of targets from the average number of observed targets. In the neural evolutionary approach, design process, employing a simple genetic algorithm oriented in real time by the entry of target gene in the environment. We try to select the hyperparameters for the RGNs that entitle the best target gene performance. As in the CMOMMG, the standard environment in the CTDR problem is a continuous 2D non-toroidal rectangular field obstacle field containing any observer agents and any target agents, so that n less than m. However, in CTDR Urban 3D, we modified the environment to continuous 3D toroidal parapiped space with obstacles. The velocity of targets is lower than the velocity of observers. The UAV's robots try collectively to move and remain with a range of observation to maximize the average number of target robots observed. A note. The next position of each UAV agent is computed by a only UAV observer coordinator agent of the hierarchy that computes and sends the new destination position to each observer agent. In the CTO Urban 3D problem, the objective of the transport targets agents is to maximize the average number of evasions of the target agents, and that is, and equal m minus a naught. The CTO Urban 3D initial approach. We have a experiment interface, ABS, agent-based simulation, and training testing in GANN in learning to predict next position of UAV observers, and experiment interface and ABS invalidate predicted next position of UAVs observers. Dataset collection. We first annotate the correct coordinate position of X, Y, and Z of the observer in question and its orientation, and the coordinate position of the 5 closest targets to him. From 22 columns defined for data collection, 19 of them constitute the set of inputs attributes, and the 3 remaining columns, the coordinates X, Y, and Z of the observer's next position, that is, the output layer. Environment. In left, vertical CTO UAV 3D scenario described in CAM, and in right, all implementation of CTO Urban 3D simulation based on WinLandscape. The CTO Urban 3D evolutionary approach. We have, again, the experiment interface, the ABS, and the training testing GANN. But now, the simple GA for the automatic designed GANN by the Ent measure. The CTO Urban 3D evolutionary approach. The node hyperparameters and the global hyperparameters to LSTM group neural networks. Learning rate, recurrent dropout, weight initialization, user bias, number of layers, layer type, layer size, layer activation, layer dropout, and optimizing. And now, the ABS and CTO Urban 3D parameters. The environment dimension, number of time steps, UAV velocity, target velocity, sensor range, number of targets, number of UAVs, K-means parameter gamma, and finally, the parameters in the simple GA, number of generations, population size, return length, random selection, and mutate chance. Experiments and results. NetLogo 3D platform was used for the agent-based simulation, that is, using agent-based simulation to measure the performance of the target gene in a 3D virtual environment that can be programmed to represent different complexities of tasks in CTO Urban 3D scenario. The NetLogo 3D platform was chosen because it allows parallel experiments and easy integration with Python for implementation of GA, more specifically the open source library Keras for the neural networks. In both approaches, the next position of the observing robots is computed employing the k-means clustering algorithm. The suspicious transport target agents employ the RGNN to predict the UAV observed next position and thus allow the targets to move in opposite direction. The RMSE value is computed by the square root of the mean difference between predicted and actual position of observers, x, y, and z next positions, in table. And in figure, we have the values of each metric for our network in 5 different CTO scenarios. Values of each measure through 2 generations. Best fitness in the CTO Urban 3D neural evolution trend graph. Details and hyperparameters to generate the best GRNN. The further brief, the model brief, the brief, and the node hyperparameters and global hyperparameters of the best GRNN. Each values attained by different approaches. The RGNN automatically assigns wins with the best edge and random adjustment and straight line the worst with the worst edge values. Conclusions. We propose a new model based on CTO, called CTO Urban 3D, for 3D agent-based simulation with UAVs and malicious evolutionary transport targets that deviate from surveillance. We use smart targets to stimulate the investigation of new arrays to coordinate UAV observer team for surveillance tasks in urban cities, alternative to CTO hierarchy k-means. The results of the evolutionary approach for transport targets have proved to be better than other simple approaches and others that employ range-down neural networks in the CTO Urban 3D scenario, making the task of organized UAVs more difficult. The limitations found was the long training time the neural networks take in evolution. In future works, we plan to extend the model, improving the 3D environment with more reality. Maps of the cities considering lines, routes, and schedules, and experiment with new organizations like oligarchies and coalitions and teams. They are references of the work, and thank you for listening.
Thank you, Mateus, for the nice presentation and also for the nice research. This is a very fine research that is very interesting in the context of the smart cities and also in public security. We, in our lab, we are developing such research also. And we will have some time for 1 or 2 questions, any comments from the audience. So if someone can have any questions, comments. Okay, so I'll make some one question is that, Mateus, I was wondering, because you say that you try to find the orientation of the target, but you always it seems that you are using the position of the target, and you said in the paper that you are using the GPS. So I was wondering, how can you find the orientation of the target to use in your algorithm. Can you make some comment about that, about this? Could you understand my question?
So, thank you, Bruno. Thank you, Sir Rosa. The orientation of all agents is computed by the agent-based simulation. And each agent in environment have a feature with the position and the orientation of him. So you can repeat the answer, the last.
Okay. I see that you use cameras in the UAVs, but you never tell us if what kind of computer vision algorithm you are using to extract the orientation of the target. Some feature extract algorithms such as SIFT, SURF, or something like that. I mean, I know that you didn't make the computer vision treatment in your research, but since you talk about orientation and you give us only the position of the target, it is important to make some comments about this in your future work. All right? Would you understand? Okay. So we have one question from the YouTube from Harrison Edward that I will send it for you, since we're just in time to the next presentation. And thank you very much, Mateus. I hope you great success in your future job. So the next presentation will be from the presenter will be Wanderson Correia, and the topic is energy management in autonomous vessels using restricted Boltzmann machine. I think Davi, or I think I don't know if Wanderson is here to present.
Yes, Paulo. Wanderson cannot be present today, but if
All
you
right.
could please play the video and I will answer the questions at the end.
That's good. That's good. Great.
Hi. Hello, everyone. Welcome to this LARS presentation. My name is Wanderson da Silva Correia. Thank you for everyone present at the presentation of my article that I developed together with a N-Bolt team at the Federal University of Rio Grande do Norte, the Electrical Engineering Department at the Federal University Fluminense, and the Computer Departments of Federal University Fluminense. I would also like my esteemed friend André Dantas, who encouraged me to write this article. Energy management. The management of energy in autonomous vehicles is an essential part to guarantee the autonomy and longevity, especially in autonomous sailboats. In this work, we propose a methodology for the application of the restricted bolt machine on an autonomous sailboat. On the right, you can see a F-bolt, a vehicle of new implementation of my code. The purpose of the algorithm is to create an automatic energy distribution system manager of the vessel, seeking to turn electrical components on off and measuring energy consumption in relation to system recharge, using solar panels. A good way to understand the project would be, imagine a mission where the vessel will take 1 hour to completing in normal condition, wherever at some point along the way we run out of wind and it's necessary to turn on the engine. Estimating that the engines will be on for the rest of the mission, the management will detect that regarding the incidence of sunlight, we would have energy for more hours, allowing the complete the mission. Or the opposing happens in the mission, that we started with little wind and that in the middle of the journey we start to have strong and more favorable winds. The engine will shoot down as the estimated of the success with the mission period would be sustained. This type of neural networks is applied as follow. Here are 2 neurons that will represent the input base, and here we have another layer we call those hidden neurons. And here we already realize that they have an architecture. A little difference from the traditional neural networks, and here in the sequence we have the connections and realize that everyone connections. With everyone include the mods of the input layers nodes that they linked with all nodes of the hidden layer. The information returned to the input layer, that is the input will update, that is we will not have a constant input. It has no output layer, we only have this structure, and the promise is that input nodes also generate data. And the main purpose of this type of algorithm is that it will describe the states of the system, adjusting the system weights. And as this type of technique is part of unsupervised learning, remembering, is that type of learning that does not have the figure of the supervisor. There is no class for the given records. You don't want to make any kind of prediction. You will use this technique to monitor the system after training. It will adjust the system status, and with that we were able to detect some outliers that would be recorded outside of the pattern. Restricted both machine. We saw that the classic representation is that all neurons bind to all of them. However, we will use a restricted both machine that has no connection with the visible layer neurons, and there will also be no connection with the hidden layers neurons. For us to research the goal, we will use divergent contracting. We will have that the learning process consists of the weights are calculated. The idea of initializing the weights is similar to what we will have in other neural networks. So what will happen, and that it will calculate a value and generate a reconstruction process. Having calculated the values, he will reconstruct the input records, and again will redo the process, take the new inputs and recalculation the hidden layer weights. That will make the mathematical calculations and again reconstruct the data, and make this repetition at the process until a certain number of epochs, or until the values of the last repetition are equal to the original input data, as if it were a dimensional reduction. There is 6 input data used with when normalized generated 15 values to be used in input layer. Limited amount of epochs to 5,000 epochs. If it reached this value, the experiment would be considered its failure. We initially tested using half of this value as hidden layer rounding up 20 neurons in the hiding layer.
Sorry, Bruno.
However, the code at all times did not find a good way to be used. So we applied some amount of neurons to...
I'm sorry, I don't know what has happened, but I think... okay, so now I can see in which slide it is frozen. Can you still hear the video or no?
Yeah, we can hear. You
can hear, but the slide is the same. Is that correct?
Yes.
At least in my playback here, it is okay. The slide that's being shown on YouTube is the same that is being played here. So I don't think this was
okay.
Was a problem now.
So let's continue. Just like this.
Okay, Paulo, I'm resuming playing.
Thank you.
Hiding layer 15.5, we've made the system stabilized with 4,903 iterations. Talk about the data obtained in the growth, the green line represents a real use with 24 hours starting at midnight and around wake in the morning. The engine is started and 10:30 off, continuing to consume only electron devices. The yellow line is the sum data on adding the estimated recharge values of a solar panel on a sunny day with a few clouds. The red and blue lines value are the data provided by the neural networks without knowing the original values, just with the inputted data. Note that although the results contain a lot of noise, it is possible to see a trend in energy consumption, and the average values of this trend come very close to the original values. For future work, we are developing the model to make it more intelligent and integrate with other sensors, thus making it possible to detect other changes in the environment, such as tidal variation. Implementing filters such as a complementary filter or a Kalman filter to improve the value of the data provided, and the adaptation and the implementation on other vessels. Thanks a lot, and I wait for questions. See ya.
Thank you, Wanderson. And so it's a very nice, interesting work. We have some time for questions for Davi dos Santos, that is also a co-author of the work. Is there any question, any comment for Davi? Well, so as I said, it's a very interesting work, and I know from Luis Marcos and also from Esteban that the final goal of this research is to make this boat, this vessel, to autonomously sail from Natal to Africa from the ocean. So I hope in near future that you can do this in this research. But when I was looking for your electronic scheme, I also could see that you use many redundancies in the sensors. For instance, you use a Navial 2, yes, and also a Pixhawk, pack. And besides, you have a GPS and an IMU. So I could not understand if you are really having this approach in the embedded electronics redundancy, or you are just putting these systems in different approaches in your vessel. So the question is, why do you use the Navial 2 and also the Pixhawk as an autopilot?
Okay, I think the idea was to, at least in this part of the work, to account for as many hardware as possible, because in the system itself, we have to have some kind of secondary systems that improve the robustness. But in this first phase, we are using only the PixHawk now. But when they were accounting for the energy part, they idealized a more robust system, and then accounted for more stuff. But at the moment, it's only PixHawk, and yeah, the other sensors like the GPS and the IMU already come with the PixHawk. Normally, when you buy a PixHawk, it comes with the kit, and some parts of the kit is a GPS and also the internal IMU, and also the Navio already also has some sensors embedded.
All right, thank you very much. Is there any further question or comments for David? Okay, is there no questions also in the YouTube? So we are going. Thank you very much, David. I hope success in your research. It's a very nice topic to research in autonomous robots. And we are going to the next presentation and the final presentation for this section. That is autonomous and collective intelligence for UAV swarm in target search scenario. I think the presenters are Flávio Souza and Luis Giacomossi.
Hello, everybody.
Hello, guys.
Paulo, could you please present our video?
Yeah, I think you.
Thank you.
Let's start. Okay.
Hello, everybody. I am Flávio Souza from Brazil at CITA. I am a PhD candidate.
Hello, my name is Luis Giacomossi. I'm a grad student at ITA, and in this video, we are going to present our paper entitled Autonomous and Collective Intelligence for UAV Swarm in Target Search Scenario.
This is the overview of our presentation. We begin with one introduction of context. In the sequence, we present the theoretical background related. Then we talk about the scenario of interest. Then we present the decision-making developed in this study. Thereby, we discuss the experiments and results of this work. And we finalize with a conclusion and future work. Swarm is a natural phenomenon of some groups of animals. Through simple rules, swarms entities manage the move in the space. The application of UAVs as swarm has been gaining attention and interest. However, this approach has many issues is open, with the capability to communicate between UAVs of swarm. The highest level of UAV swarm autonomy is the ability to perform a task coordinated among multiple UAVs without the intervention of a human operator. An important application is a search for targets that we cover in this work.
To model UAVs, we mainly apply two techniques. First, we introduce the steering force model. This method is used to guide the drone to a target by a simple sum of vectors, resulting in a vector force that is applied to the UAV model to guide this UAV to the target. We also have used the potential fits technique. It's a very traditional technique and used a simple variation using the equation of a normal variate function. A velocity field is created by taking the partial derivatives of this function, and then we can apply it as a collision avoidance method for the UAV. Using UAVs for search applications is not a new concept, but using several UAVs forming a swarm is still a not fully explored concept. Alnon and Cruz studied the usage of heuristic algorithms for search tasks using UAV swarms, and they concluded in their work that the search by line is the simplest and most efficient search method. This is the method that we are going to explore in our paper. Here the agents are going to be distributed by the lines of a discrete map, and they only progress by searching in not visited cells. We propose a scenario where a UAV swarm is applied in a search mission to find a missing individual. We assume that UAVs do not have previous information about the position of this individual. We also assume that the target is considered found when a UAV is in a range less than 20 meters of this target, considering that the UAVs are capable of identifying the target using a vision system. The last assumption is that the drones can communicate using a common network. So for this paper, we have developed a simulator to properly evaluate our methods. This simulator was developed in Python using the Pygame library. In this picture, you can see the simulator view. The UAV swarm is searching for the target, and there are obstacles in this scenario that UAVs must not collide. The decision-making that we developed in our paper can be divided in two categories: autonomous intelligence regarding a single autonomous UAV model, and a collective intelligence, since we are working with a group of drones. There are 6 models in total, 3 to each category. In autonomous intelligence, we have the target search model that is responsible to perform the search and selection of cells in a discrete map. The behavior model uses a state machine to control the autonomous behavior of a UAV. And a collision avoidance model is used to protect and preserve the agent. Now, as collective intelligence, we have the swarm search model that is responsible for mapping the regions that were not visited by the group in a discrete map. The blockage prevention model prevents the drones from getting stuck in regions of the scenario. This problem is common when using potential fields. Mission closure model: when a UAV finds the target, the coordinates are going to be shared to all the drones using the common network, so all UAVs can now move to this position. We have developed a state machine to control the autonomous behavior of the UAVs. This machine is seen in this figure. A copy of this machine is present in each drone. There are 4 behaviors: search target, seek state, go to the closest drone, and run on target. The default behavior is the search target. In this state, the UAV will perform the search for the individual. When the individual is found by a member of the swarm, the machine will transit to the seek state. Now the search stops. In this behavior, the UAV now knows the coordinates of the target and can go directly at him. There are 2 auxiliary states: go to the closest drone and run on target. Those behaviors implement the heuristics to avoid the blockage in local minima that are present in the potential fields technique. Now we are going to show a short presentation video of our simulator running. Note that the first iteration uses the target coordinates previously known to take this time as a reference for the best case scenario, so the swarm moves directly to the target. Also note that the cells that are being visited are marked. This map is updated at each time step and is shared by all drones. Here we can see how our blockage prevention heuristics work. The drone identifies that he's blocked. That is, he's not moving by a period of time. Then he will search in the UAV swarm network for the closest drone. He then will head to his coordinates and going to be set free. When all drones are finally within the radius marked around the target, the iteration is over, and a new one will begin with a different scenario, but maintaining the same number of agents. Now we will discuss the experiments and results obtained.
We apply a statistical evaluation, a complete factorial design. Consider the three factors, vary the numbers of drones and obstacles and search strategy. Pay attention to the first level of search strategy, when we use the target location previously known as the best case reference. It's important to say that the time complete of mission metrics is when our UAVs reach the target. Here we have the result of the mission completion time metrics. In most cases, the heuristics didn't present one influence on the performance of this metric, having as reference the values in the blue. We note that in all cases, the heuristic increased the completion time metrics. This behavior is expected. The heuristic method does not guarantee optional time. We also observe a bigger difference between 50 and 30 obstacles. With 15 obstacles, the time of mission is statistically bigger. This happened because we can have more difficult scenario with 15 obstacles than with 30 obstacles. Because the targets can stay in region with very close obstacles, create big barriers. This graphic represents the quantity of the local minima in the experiments. Again, have as reference case in blue. We observe in our case that we used the heuristic there is a big reduction of the local minima. Remember that the local minima itself equals to the number of blocked UAVs during the experiments. This indicates a better efficiency in the search, with way less UAVs blocked.
In this work, we have studied how a swarm of UAVs can be used in search missions. A simulator was developed for this study. Using the simulator, we have studied intelligent search strategies using these autonomous UAVs. We have proposed heuristics to avoid the blockage of the agents when using potential fields. With our methods, we have seen that the swarm can be a very effective tool to search for mission targets. Future work should consider applying these techniques in a simulator with a realistic physics for deeper evaluation. In our work, we have focused on the development of decision-making techniques, abstracting the evaluation with a more robust simulator. Future research should also analyze how optimization algorithms can improve these results, and can also apply reinforcement learning to learn more complex behaviors. These are the references of our work. Thank you so much for your attention.
Thank you for the presentation, Luis and Flavio. Congratulations for the results. It's very interesting, very nice results, very nice simulator. And we have time for one question. Is there one question and comment? One question?
I have a question.
Okay, Bruno.
So Luis, thank you very much for your presentation. Very nice work. Congratulations. It's more of a operational and more of a curiosity too. Did you use Pygame, right?
Pygame, yes. Pygame library.
So how much work did you have to do with Pygame to apply Pygame to these drone scenarios? Did you, for example, did you have to implement or to program the physics simulation for the drones, or they are ready and you can just use it? Thank you.
Thank you for your question, Bruno. We have we had experience with the Pygame before, and we have like a small framework that we use to develop this simulator. So based on this framework that we had before, we kind of we gather all these models and we improved the simulator to implement this for this paper, right? And the biggest problem was to basically implement the decision-making techniques, not to implement the Pygame. That's right. Thank you.
Very nice, please. Thank you.
Thank you.
All right. So thank you very much for the presentation. It's a very nice presentation. And thank you all the participants that showed up for this section. And we see we are going to have the next section right now. Thank you very much. Thank you all.
So good afternoon, everybody. So Bruno, may I start now? So.
Yes, Gustavo, okay, you can go ahead.
All right. So good afternoon, everybody again. My name is Gustavo Freitas. I'm a professor from the Federal University of Minas Gerais. And I'm going to be the chair of this section, which is the second section on control and robotic systems. The first paper that we have here is the 6D robotic Graspnet system using convolutional neural networks and adaptative artificial potential fields with orientation control. So Caio, good afternoon.
Good afternoon, Gustavo.
Do you want to do the presentation in your computer? Do you want me to play the video?
I'd like to play the video, please.
All right, so go ahead.
Hello, my name is Caio Vitorino, and my advisor is Professor Dr. André Scolari, and I am a PhD student at the Federal University of Bahia and member of the Laboratory of Robotics. I'm going to present this work entitled 6D Robotic Grasping System using Convolutional Neural Networks in Adaptive Artificial Potential Field with Orientation Control. Robotic grasp is highly complex in unstructured environments such as houses or warehouses, in which the objects to be manipulated have diverse or heterogeneous geometries. The multidisciplinary nature of robotics has become the foundation of its exponential development in recent years. With the cooperation of artificial intelligence and computer vision, the technological progress observed in the area of autonomous robots, whether mobile or not, was notoriously relevant, exceeding classical methods. Analytical grasping methods are applied in unstructured environments. However, they do not have good efficiency with unknown objects and unstructured environments. These methods consider that the object's kinematics, dynamics, geometry, and position, in addition to its contact with the gripper, are entirely known, therefore little applicable to practice due to its modeling complexity. Unlike analytical methods, the need for a complete analytical model is eliminated by empirical methods. These methods use machine learning to create models that relate human-labeled data to RGBD sensor data. Techniques based on deep learning have good grasping efficiency when considering unknown objects. Through this, it's possible to extract important characteristics of the objects that help in the grasp generation, surpassing the performance and robustness achieved through empirical and analytical methods. Robotic grasping had been applied in practice since 2015 by Virek, Male, Jones, Levine, Pinto Gupta, Lenz, and so on. But this method had low computational performance. Morrison tried to solve this problem by proposing a small CNN called Generative Grasping Convolutional Neural Network, or GGCNN. This network generates only one grasp per object, and it does not check for collision with nearby obstacles. In other words, if you are trying to grasp a specific object in the workspace, the robot can hit another object. This method also generates only planar grasps. This is the image of the simulation that we performed in Gazebo, and it's the image from the simulation in Arvis. Mozavian proposed a new CNN called Graspnet. The difference between Graspnet and GGCNN is that Graspnet is capable of generating multiple grasps per object. It also generates 60 grasps. However, it's unable to filter or recognize the object by its point cloud, so it depends on an object segmentation technique. As you can see in the image, if we use the point cloud of the environment as input to the Graspnet, it would generate a set of grasps in the entire workspace. So we need to filter only the point cloud of the object and use it as input to the Graspnet. We are applying autonomous grasp in an additive manufacturing unit. So the position and orientation of the object are unknown, as well as its geometry. Also, the position and orientation of the printer are completely unknown by the robot. To solve this problem, we propose the integration of a convolutional neural network to recognize the object and select the object's point cloud. We are also applying a grasp generator algorithm capable of generating multiple 60 grasps per object. We also developed a heuristic method to filter the grasps generated by Graspnet. We integrated a collision avoidance technique with orientation control to reach the position and orientation generated by the grasp generator algorithm to avoid collision with nearby objects. Graspnet is based on variational autoencoders. So the authors used the PointNet++ to extract features of the object's point cloud and generate new grasps based on the ground truth grasp. In this technique, we construct a latent space that's normal. For that, we use the Kullback divergence to ensure that the latent space is normal. And also, we apply a reconstruction cost that compares the position and orientation of the generated grasps with the ground truth grasp. In the inference process, we just need to sample from this latent space, and we also need the object's point cloud and the gripper geometry. By using that, we can generate a set of 60 grasps, as you can see in the image. In order to reach the position and orientation generated by Graspnet, we used a technique called Adaptive Artificial Potential Field with Orientation Control. We developed this technique and published the results last year. So if you are curious about this method, please check out the paper, or you can use the QR code to watch the experiment videos and also the presentation. To test the performance of our grasping technique, we used the objects that were proposed by Mahler. So these objects have a complex geometry and they are highly difficult to grasp. These are the configuration that we use to run the convolutional neural networks. And to test the robotic grasping technique, we used the virtual model of the UR5 from Universal Robots and also the Robotic 2F140 and the DefCan Intel RealSense D435. Before showing the actual video experiment, I will briefly explain the grasping pipeline. First of all, we get the initial state of the robot called GA. In this state, we get an RGB image of the object that's on the printer bed. This image is used to generate a mask in stage 3. In stage 4, we copy the mask that's on the RGB image to the depth image. In stages 5 and 6, we transform the depth image pixels into point clouds by using the back projection algorithm. But the point cloud have outliers that are removed by using a statistical filter. In stage 7, we get the point cloud of the environment. In stage 8, we downsample this point cloud. A grasping generator technique called Graspnet is used in stage 9. But as can be seen in the paper, we have a lot of grasps that collide with the point cloud. So we need to filter these grasps in order to obtain a viable grasp that do not collide with the environment. To do this, we check if there is any point of the point cloud that is inside a collision mesh of the gripper. In stage 13, we downsample the point cloud obtained in stage 7 in order to put the repulsive fields. These repulsive fields are used by the Adaptive Artificial Potential Field algorithm with orientation control. The final grasp is shown in figure 16. By applying this method, we avoid not only collision with the point cloud with near object, but also with objects in the path to the grasp pose. Now I will show you a video that demonstrates how this grasping pipelining works. We performed 30 grasps per object to test our grasping performance. As you can see in the image, we could achieve a high grasping success rate for the vase in part 3, but for part 1, this is a small object, we could not achieve a high grasping success rate. Also, these objects are highly complex to grasp, but Graspnet was trained only to perform grasps in simple objects such as bounds and boxes. Considering the grasps performed, 15% failed due to the path planning algorithm, 11% failed due to a non-successful detection, and 50% failed in consequence of the grasp generated applied. It was noted through experiments that Graspnet has lower performance with small objects. Also, the collision check system based on point clouds avoided collisions inside the 3D printer. The AAPF with orientation control avoided collision when the collision check system failed. Here are our thanks and the references, and thank you for your attention.
So Caio, nice presentation. Congratulations. Do you have any question from the audience, from Zoom or from YouTube?
I have a question.
Go ahead.
Thank you. Caio, when you introduced the Graspnet architecture, I realized that it was a probability function graph, and I'm interested about it because these probabilities refer at the moment of the latent space generates an approximation, or if so, how can this information be structured from the network in probability form? I don't know if you understand what I'm questioning.
Just to see if I understood, how can I take a sample from the latent space to transform it to the grasp pose?
Yeah, but the sample, I'm talking about the PDF, the probability density function. Because in the graph, when you introduce the Graspnet, have a graph of probability in there. So I'm curious about it. How do you extract this kind of information? Do you know?
Okay. So in the process of building the latent space, it's done by simulated grasping trails, right? So when the robot is trying to grasp a object in simulation, it acquires the object's point cloud and also the position and the orientation of the grasp. So if the grasp succeeded, this information, taking into account the point cloud in the position orientation, is stored as a function into using the Kubrick library divergence to the normal space, to the latent space, to ensure the normal distribution. So that's why in the inference process we need these information also to generate new grasps, because only the probability is not sufficient. We also need the point cloud of the object and the position orientation of the gripper. So these information are related using the network. You know, we don't really know in depth how these information are related because it's part of the network. And all these weights we know, so it's part of the training process. But I mean, only the probability is not sufficient. It's just part of the process. I don't know if I answered the question.
That's okay. Thank you.
So Caio, one fast question here because we are running out of time. So you did the training of the network. We using which data set?
Actually, I did not train the network because the author used a powerful hardware to train these Graspnet. I mean, they used more than 10 million. They sampled more than 10 million grasps using a lot of objects. So I don't have such a computational power.
And if you need to change your gripper for a gripper with 3 fingers, so you need to train the network, the Graspnet, all again?
No, we just need to pass the new gripper geometry to the Graspnet so it can see the points of interest of the gripper. And when it sees a new point cloud, it can relate the point cloud of the object and the gripper geometry. So it's highly dependent of the gripper geometry. Unfortunately, we can't use a unknown gripper as new methods are trying to do.
Oh. All right, thank you. I have more questions, but we are running out of time. So thank you again, Caio. Congratulations for the nice job.
Thank you.
So now we're moving to the second paper, development of a wearable under-actuated finger exoskeleton for haptics, preliminary formal results. Hi, Gilberto, good afternoon. Do you want to present in your computer or do you want us to play the video?
Let's play the video, please.
All right, so guys.
Good day, everyone. I'm Gilberto Alexis Reyes Perez, master student in robotics and advanced manufacturing in the Research Center for Advanced Studies. And I'm going to present you my work titled Development of a Wearable Under-Actuated Finger Exoskeleton for Haptics, Preliminary Formal Results. This work was made in collaboration with Dr. Nadia Vanessa Garcia Hernandez and Dr. Vicente Parra. In this work, we present a wearable index finger robot with haptic purpose. This design is inspired in ExoTrack, a wearable hand exoskeleton that uses external kinematic change as power transmissions. In this work, we adapt the exoskeleton as a haptic device. Also, we present a dynamic analysis where we propose the exoskeleton as a cyber-physical system. Here we can see the table of contents that we are going to review, and starting with a brief introduction, the exoskeleton technology is not new. There are decades of previous works about this topic. Nevertheless, despite the interest in robotic exoskeleton systems, there remains key aspects of basic and applied research, such as physical human-robot interactions and embodiment for the wearable exoskeletons. And that's why we keep in the research about exoskeleton designs. The functionality of an exoskeleton should be rational apart from robot and should be subrogated wearable system. Its kinematics must yield an unconstrained range of motion when the user places its fingertip in the end effector of this device. In this slide, we can observe a side-to-side comparison between the original design and the design that we present. Here, we can observe that the kinematic change remains as the same for the index finger, but everything else is different, including the actuator, microcontroller, and the circuit. Well, the most notable difference is that the new design have only one kinematic change allowed. Here we can see how it was modeled and its dynamic hardware values. We believe that this kind of mechanisms are the best to its properties of flexibility and adaptability. At the moment for the index kinematic change, we use AS5045 absolute magnetic encoders of high resolution that allow us to obtain the generalized coordinates of the kinematic change. These encoders can be serially connected, reducing the inputs and outputs of the system. To the right side of this slide, we can observe each position of these magnetic encoders through the kinematic change. For the reading of the encoders, we use an embedded board Nucleo 144 STM32. This board was selected to its processing and velocity properties, allowing us to reach low latency required for this kind of haptic systems. Also, with this device, we control the actuators, which is a micromotor Fauhaber of 1319 series. This motor comes with a planetary gearbox of 246:1 ratio of reduction, which allows us to reach a stall torque of 0.72 Nm. and it have attached an encoder with a resolution of 63 microradians per lecture. Also, we use the Nucleo board to control this motor. To control this motor, we use a PI control current loop in torque mode. For the current feedback, we use an ACS 712 current sensor, and for the control constant, we use the pole location method, where we search for a critical damp response, with a natural frequency of R divided by L, where R is the resistance of the motor and L the inductance of the motor. And finally, we obtained values for constant P and constant I, where Kh is the amplified constant of the H-bridge circuit and key S is the constant for the feedback amplification. And that will be all for the physical system. Also, part of the contribution for this work is its dynamic analysis. The dynamics for this kind of systems are rarely studied, focusing only on the robotization of the exoskeleton. In this case, we find convenient to point that this kind of systems is modeled as a nonlinear constraint Lagrangian robot, where at the left side of this equation we have the endogenous forces of the system, like the inertia matrix, Coriolis matrix, gravity vector, and the friction. And to the right of this equation, we have the exogenous forces, where we have tau h as constraint forces, like the force of the finger that is attached to the end effector or the contact with a virtual or real object, where J is the geometric Jacobian and lambda is the Cartesian force at P independent contact points. Tau is the control torques vector with B as an input matrix and tau being the vector of control inputs. Since we only have one actuator, this control torque vector ends with only one element on the first position of this vector, which is the desired torque multiplied by the reduction for the motor. And tau h is the human forces that the user introduced into the system. Such forces can be written in generalized coordinates, as we can see here. We can observe that in this case, the human force have presence in all the values of this vector. It's divided in the 6 elements of this force vector. From previous definition, we can identify human forces as control torques, giving a cyber-physical system where the control torques and human forces collaborate at motor level. In this way, the cyber-physical control provides full actuation despite the unique motor actuator. Here in the 8th equation, we can see how the torque of the motor and the torque of the human are combined in the first element of the input torques for this cyber-physical system. To prove that, consider the case where the exoskeleton is weird and in a static pose. Here, the motor torque is 0 and the velocity and friction are 0 too. In this condition, the human user is who provides the force that compensates the gravity force. So we can summarize that the human user actively participates in the control of the device to maintain an static pose. We can see that the only reasonable way to explain this effect is that the human managed to compute at each time to inject the exact force proportional to the exoskeleton gravitational torque, as we can see in the 10th equation. At last, to prove its functionality as haptic device, we present two tests. The first test have the objective to demonstrate that the device is capable of reaching all the range of motion of the finger, despite the size of the finger. For that, we create a kinematic simulation of one human finger attached to the exoskeleton and move the finger in all its range of motion to see if the kinematic change was capable to follow the movement. We did this 2 times, one for a short finger with the dimensions shown in table 3 and one for a long finger with the dimensions shown in the same table. We can see here the parameters that we use for the experiment in the range of motion and for the size of each phalanx for each finger. So these are the results for these experiments, where the green dots represent the fingertip position in the range of motion for the long finger and the red dots for the short finger. In each position, the exoskeleton was capable to follow up the finger movement without causing any constriction. That includes the extreme cases of total flexion and total extension. From this, we can summarize that the exoskeleton provides a full range of motion for the finger without causing any constriction for the user. And for the second test, we have the objective to validate the exoskeleton as a haptic device. So we develop a virtual environment in Unity 3D where we put two objects with different stiffness. The red object comes with a spring value of 100 and the green object comes with a spring value of 50. To the left of this slide, we can see the configuration of the experiment that simply consists of touching both virtual objects with the device to see what kind of haptic sensation provides. In this figure, we can see the penetrating distance for the interaction with the more rigid and the less rigid object. In this, we can see the desired force vector that we compute with the proxy method, where we can appreciate that the desired force splits in X, Y, and Z axis. And we can see that the desired force vector for the more rigid object was even bigger than the less rigid object, despite the penetrating distance. Here we can see the desired torques to render the haptic feedback in each generalized coordinate, but in this case we only care for the torque of the first joint, that is the torque 1 or the blue line. And finally, we present a comparison between the desired torque and the current that passed through the motor at the same time, where we can observe that it's pretty close, so we can summarize that the exoskeleton is capable to provide haptic sensations. Also, note that the penetrating distance for the less rigid object is almost twice that the required for the more rigid object, demonstrating that the haptic sensation will be proportional to the virtual object characteristics. And basically that will be all the work covered for this article. At last, we like to discuss that the development of a hand exoskeleton stands for a challenging issue to its high complexity and requirements. The human in the loop must be considered in the analysis of the system because its active participation is not negligible. So, in this way, the system can be considered as a cyber-physical system. Finally, the device presented here is an index finger wearable exoskeleton with open architecture that allows full range of motion of the user finger and it's validated as a haptic interface. And that was demonstrated with the results of the two tests shown. Also, the 6-dimensional operational force exerted by the human at the end effector are propagated as human control torques complementary to the torque generated by the motor at joint 1. Also, I would like to mention some limitations for this device. Well, the limitations for this system is that due to its height under actuation, we cannot render haptic force in all directions. We only have one kinematic change, and there are not psychophysical tests that validate this work. As future work, we already plan to add at least 2 more fingers for the middle and the thumb. Also make psychophysical tests to prove the usability for this exoskeleton, and also to optimize the mechanism design for a better performance. And that will be all by my part. Thank you for your kind attention. Now I will gladly answer some questions.
Thank you, Gilberto. Congratulations. So do we have questions from YouTube, questions from Zoom? Well, I have some questions here, Gilberto.
Yes.
So first of all, you said in the conclusions that this is an open architecture. So
Yes.
Can we download the new projects that you developed, like online? Are they available in the internet?
They are not available yet because this work was paid by my scholarship in my university, so all the codes remains for the institution. So I couldn't upload those codes, but the code
like
is
the project, the
yes,
3D printings.
yes.
All
It's
right.
property of the university.
So it's not a really like an open architecture. Well, it's for you.
Yes.
Other question. Usually, I'd like Daniel here wants to ask a question for you. So Daniel,
Yes.
are you there?
Yes. Thank you very much. Congratulations for the work. I would like to ask a question with respect of the finger. It is an underactuated system. Exactly. So have you planned in the future to make some kind of control for this underactuated system? Have you planned, or are you planning to design some kind of control for the underactuated finger?
Well, at the time, we only have the control for the motor where we try to render this haptic sensation with the touch of a virtual object. So we are pointing where the human user completes this control in the analysis of the dynamic system. So, well, the high underactuation of these systems represent a really complex problem for control the entire kinematic change. So we are more focusing on these problems.
Sure, sure. Okay, thank you very much.
Thank you.
Thank you, Dan. Gilberto, one last question, really quick. Usually haptic devices are quite expensive. Do you have an idea of the cost of your prototype? You don't need to be precise.
Well, all its elements should be around, I don't know, like maybe $500. But in comparison with the exoskeleton that are already in the development, it's like $700 or something like that. It's really, really expensive, this kind of device. So when we only use one motor, we are reducing in very high way the cost of this device.
I see. All right. Again, congratulations. That's a nice work with a nice prototype.
Thank you.
Thank you, Gilberto. So let's move to the third paper, which is the constrained control of non-holonomic mobile manipulator by explicit reference governor. So Luis, are you there?
Yes.
Luis, do you want to do the presentation in your computer? Do you want us to show the video?
I want to show the video, but I want to know if Bruno received the second video I gave him. Because the first one has a problem.
I saw your video yesterday, and yes, there was a problem. I haven't checked it today.
Okay, you can play the video.
So let's see. Bruno, can you play it?
Good evening, everyone. My name is Luis Raja, and the theme of this presentation is Constrained Control of Non-Holonomic Mobile Manipulator by Explicit Reference Governor. Mobile manipulators are a class of industrial robots, and it's basically the union of a robotic arm on a mobile basis. Mobile manipulators play an important role in logistics, within product warehouses, exploring nestable and dangerous locations, and more. However, it's not an easy task to control or navigate them. They have singularities and non-linearities. Moreover, while moving, they need to avoid obstacles and restrict areas. So the goal of this article is to design a constrained control system capable of navigating a wheeled mobile manipulator by avoiding singularities and constraints with a low computational cost. And for this purpose, we employ the explicit reference governor. The explicit reference governor is one recent alternative solutions to constrained control problems that provides a suboptimal but analytic solution. Its basic idea is to dynamically change the reference signal of a pre-stabilized feedback control system to deal with constraints. So it's basically change the reference input to give a modified reference for the closed loop system, given by the states of the system and the modifier reference. The summary of this presentation is system model with system description, dynamic modeling, and inverse dynamic control, explicit reference governor with description, dynamic safety margin and potential fields, implementation with types of constraints, project implementation and results. The system is described as a mobile manipulator with a non-autonomic mobile basis and a two-DOF planar robotic arm. The base restrictions are given by the matrix A, and the mobile manipulator is completely described by these seven variables with vector Q. The dynamic modeling of the mobile manipulator is given by the Euler-Lagrange equation, but it's not proper because of the lambda term is not trivial. So we have to modify the Euler-Lagrange equation to a new one based on using the null space of matrix A, which is the S transpose, by multiplying it and changing the vector Q to Z dot. We have the new closed loop system in restricted space, and it's given by this figure. The final step of the dynamic modeling is to modify the closed loop system representation from the restricted space to the workspace. And to do that, we must find a Jacobian which represents the mobile manipulator to the injector of it. And after find it, we multiply the latest equation to Jacobian transpose and modify the variable z dot to the x dot related to the velocities of the injector of the x and y position and the mobile basis of the x and y position respectively. The inverse dynamics control is pretty straightforward. We just need to find a nonlinear input for the system to give a linear output, which is the AX. And to control it, we use the KP and KD gains related to the position and the velocity of the system, and the reference input, which will give us the desired position, velocity, and acceleration of the mobile manipulator. And it will give us the error formulation. And this is the closed loop system representation in task space with inverse dynamics control. The explicit reference governor is essentially a reference modifier. It stays between the reference input and the stabilized system. And the goal of the explicit reference governor is to create a new reference which will avoid the constraints that you give to it. And there are two essential parts: the dynamic safety margin and the attraction field. The dynamic safety margin is how much your system can go without encountering the constraints that you give to it. And it's given by V, which is a Lyapunov function of the closed loop system, and gamma, which is the largest invariant level set of the system. And for mobile manipulated case, the value of the inertial matrix M changes over the movement of the robot. So the largest invariant set is given by the second equation, which is based on the minimum value of the matrix, the inertial matrix can get. The attraction field is the direction to be taken so that the current reference meets the desired one without going through restrictions, as shown in this figure. So it's basically divided in two parts, the attraction term, which is whole R, and the repulsive term, which is the whole 0. For the project implementation, we use two types of constraints. One is a positional one in the y-axis for the end effector do not surpass it, and the singularities of the mobile manipulator occur when theta 1 is equal to plus or minus theta 2. So with some simulations, we find that these singularities occur more often. These singularities occur often when the end effector and the mobile basis axis are less than 0.2 or greater than 1. And this is the table of control gains given to the system. The results are as follows. The first simulation tests the mobile manipulation trajectory within constraints to compare with mobile manipulation without it, without the ERG control. So given a reference and the V are actually the same and the trajectory are the same. It's because if there is no restrictions in the trajectory itself does not need to change. The second simulation tests the positional constraint. So I give a reference position in 1.2 y for the end effector. So the end effector should surpass the constraint 1, but the mobile manipulator with ERG does not surpass it. The third test is the minimum value constraint simulation. And if a reference in 0.2 modulus, they give us a 0.23 modulus for the minimum value. And the fourth test is the maximum value constraint. So I input reference in 1.2 for the desired, and it gives us a modified reference with 0.9 modulus between the end effector and the mobile basis Cartesian taxonomy position. And thank you very much for your participation.
So thank you, Luis. Congratulations for the nice paper. Do you have questions? Since we don't have questions from YouTube, do you have questions from Zoom? So I'm going to ask you some questions. The simulation results that you show, have you got them using MATLAB or other software? Maybe
using MATLAB.
Simulation using MATLAB. All right. And are you planning to go to other simulations or simulators where you could build the entire robot, the mobile platform, and the arm, like Gazebo or Papelacin, Webots?
Yes, we are trying to implement in Gazebo, ROS Gazebo. And maybe why it's a 2D mobile manipulator, we could try the PyGames that the other presentation did.
Yes, could be a solution. And regarding that, Luis, so you are dealing with a simple manipulator with just 2 degrees of freedom and a mobile platform in moving on a plane. So what will be the difficulties to use a manipulator with extra degrees of freedom, maybe a 6 degrees of freedom manipulator, and also moving in a 3D terrain?
I think the most difficult part is to both write the Lagrange equation and then transfer it to the delta part of the ERG control, because it's based on the inertia matrix of the closed loop system. So, and with that, we have to adjust the control gains and so on. So it's not an easy task, but I think we can do it.
Well, yeah, we hope to see the results. And do you have a real platform that you could try and you could execute your algorithms?
Yes, I have, but the control that I implemented, it's not that good with errors and disturbances. So we must change the type of control and maybe have some improvements in the ERG control to actually try one real mobile manipulator implementation.
I see. Well, good luck in your future work. And again, congratulations, Luis.
Okay, thank you.
So let's move to our final paper in the section, which is Proposal of Multi-Modal Robotic Architecture Considering Social Constraints Applied to an Intelligent Wheelchair. Vinicius, are you there?
Yeah, I'm here.
So Vinicius, do you want to present in your computer? Do you want me to play the video?
Play the video, please.
All right.
Thank you. Hello everyone, my name is Vinicius Viana Moitinho, and I will present the work Proposal of a Multimodal Robotic Architecture Considering Social Constraints Applied to an Intelligent Wheelchair. This work was developed by me, Vinicius Viana Moitinho, Félix Brito, José Dias Amado, Vitor Costa, Daniel Souza, Elvio Prado, Cléa Libarino, and João Erivando Soares. This research was supported by the public call Seleção de Projetos de Apoio ao Empreendedorismo Inovador com Foco na Economia 4.0 through the project Intelligent and Autonomous Motorized Wheelchair and also by the Grupo de Inovação, Pesquisa e Automação Robótica GIPAR of Instituto Federal da Bahia, IFBA. Making a contextualization of the work, an autonomous system is composed of several components, such as sensors and actuators, the perception parts, navigation, control, among others. Therefore, it's necessary to develop an architecture project that allows a broad view of its operation and its organization. In this work, a software architecture was developed for autonomous wheelchair, but with particular features related to human behavior. This architecture allows the autonomous system to perform its functions, considering the feelings of the people around and the user, which increases their safety and well-being. Taking as an example of a circumstance where it's necessary to increase the speed of the wheelchair, and the user shows a feeling related to fear. So the tendency of the system will be to slow down and return to the previous speed, as shown in this figure, where the wheelchair speeds up and the user is scared, so the system will slow down. For an autonomous system to fulfill all its goals, it requires a core set of algorithms and technologies that can be categorized into perception, planning, decision-making, and a human-machine interface. Thus, autonomous systems use several sensors to measure data from external environments, which are manipulated by perception algorithms to summarize the data into useful information that are used by planning and decision-making algorithms to then reproduce commands to be followed by the actuators. To perform the organization and determine how these algorithms work, a software architecture needs to be implemented. So, the architecture proposed by this paper were organized in layers that contains groups of components in common. This distribution is made by 6 layers: sensors, perception, database, planning and decision-making, system management, and control. Separating the architecture into layers increases the flexibility and the scalability of the architecture, as this method of organization allows the replacement of one or more components of the layer without compromising the operation of the system, as long as the communication interface with other layers is maintained, of course. For ease of understanding, let's look at the architecture separately. The first part of the architecture is composed by the sensor layer, perception layer, and the database layer. The sensing layer is composed of a set of sensors in charge of measuring the surrounding data of autonomous system. The main objective of this layer is to obtain data to be interpreted by the perception layer, ensure that the system can obtain a representation of external environments with a certain level of accuracy. The perception layer is responsible for converting the data obtained by the sensors into useful information and enable the autonomous system to create a representation of the surrounding environment. This layer is composed of SLAM, user perception, social perception, and environment perception. The SLAM is in charge of making the mapping of the sites and the localization of the system that is important to determine the beginning and the end of the goal set by the user. The user perception component is in charge of analyzing the data obtained by the system user-oriented sensors. It includes a group of algorithms capable of identifying with a certain level of accuracy the feelings of a human being. Then the information obtained by the algorithms is stored by the components of the database layer and will be useful for the planning and the decision making of the system later on. The environment perception module has the objective of identifying possible obstacles in the wheelchair surroundings. And the social perception module aims to analyze people around the system, based on some factors such as face, speech, as well as taking into account other social constraints present in the location, such as sex, age, gender, culture, and nationality. All the collected information is stored in the database layer of the architecture. So this first part of the architecture can be summarized in collect, interpret, and store. The second part of the architecture is composed of the planning and decision-making layer, the control layer, and the system management layer. The planning and decision-making algorithms are essential for the correct operation of the autonomous system, because they are responsible for verify all the information considered by the components of the perception layer and determine the actions that will make the autonomous system accomplish all the objectives. In the proposed architecture, this layer is divided into two components. There is the route planning and the social behavior planning. The route planning is the main component of the planning and decision-making layer, because it is this component that verifies the information provided by the other layers and defines all the actions to be performed by the system. On the other hand, the social behavior planning has the objective of verifying the information coming from the components of perception layer in the social scope, and feeds the route planning with action to be taken. So, this component analyzes the condition of the feelings of the people around and of the system user itself, and if necessary determines actions to be followed by the system. The system management layer groups some components in charge of some fundamental functions for the system in general. In this layer are present the components human-machine interface, global interface, and monitoring system. The human-machine interface has the objective of intermediating the communication between the autonomous system and its user. It is through it that it will be possible to stipulate the goals for the system to accomplish, and also transmit information that may be useful to the user by means of interactive chatbot. The global interface performs a communication role of the autonomous wheelchair with other systems. This component enables the use of two important functionalities for the intelligent wheelchair. The first one is the exchange of useful information between two similar systems. And the second one allows the control of the objective to be followed by the autonomous system to be set remotely. Every intelligent system is subject to failures, and it is necessary to identify them so that can be corrected. The monitor system module is linked to this concept, and is responsible for checking the system data flow and analyzing if any unit does not behave as planned. The control layer has the objective of executing of all the actions defined by the components of planning and decision-making layer. It uses algorithms responsible for converting the decisions made into acceleration, braking, and steering commands, which allow the autonomous system to follow the necessary trajectory to reach the determined goal. So, this second part of the architecture can be summarized in plan, execute, and verify. The proposed architecture for the intelligent wheelchair presents a series of functionalities and technologies that make it possible to implement a multi-modal system according to the needs of the user. The system provides three control modes with varied levels of autonomy: the manual mode, the autonomous mode, and the social autonomous mode. It is essential to have a way to control the system manually, and in the case of the manual mode of the proposed wheelchair system, there are two ways to execute this functionality: by the joystick on the wheelchair, or by pre-established voice commands directed to human-machine interface. Although social perception is a very important tool that assists the intelligent wheelchair, there are situations in which the social perception algorithms may present inaccuracies in the operation, such as environment with a lot of people. So, the autonomous mode of the wheelchair has the main features that an autonomous system needs. However, the social perception modules are disabled. In this way, social aspects are not taken into account in this operation mode. And the social autonomous mode of the wheelchair represents the standard operation mode of the system, in which all the functionalities described in the software architecture are used. So, in this control mode, the people around the wheelchair are taken into consideration when planning and making decisions about activities. The figure shows the components used in each mode. As future works, the proposed architecture is being implemented through the Robotic operating system, and with this, it will be possible to analyze the behavior of the system empirically and make, if necessary, modification in its structure. Thank you for the attention, and if you have any questions, you can contact me by email.
Well, thank you, Vinicius, for the presentation. A nice work. Do you have questions from somebody from Zoom or from YouTube? So I'm going to ask you some questions, Vinicius. So the idea here of this social autonomous navigation system is quite interesting. And I was imagining some kind of situations here. So you mentioned about social perception, and you said about age, gender, and culture. Do you have any idea or one example of how these things could change the trajectory of the wheelchair?
It's some situations that if a person demonstrates a feeling, you know, a fear feeling, you know, about the movement of the wheelchair, so the wheelchair will change your trajectory to move away from this person, you know. Or if the wheelchair can analyze if a situation is a trouble for the user, you know. So when the wheelchair identifies a trouble for the user, the wheelchair will move away or return for the security of the user, you know.
I see. And I figure out that you're presenting like a high-level architecture, but do you have any ideas of which sensors are you going to use and which SLAM techniques, path planning techniques, control techniques? I know that you are like your propositions in much more high level, but do you have any idea of how to implement this and make this real?
Yes, we use LIDAR sensors, and for the social perception will be cameras oriented for the external environment and a camera oriented for the user itself, you know.
I see.
Because the user is the most important for the social perception.
All right. Well, thank you. We are a little bit late, so I think that we should finish this section. Just before finishing, I'd like to thank you all the authors and congratulate them. And I'd like to remember that today at 7 p.m. we're going to have the virtual cocktail. So I hope to see you there. And we are ending this section. Thank you, everybody.
Hi, everyone. Professor Daniel, you can start as soon as you want, okay?
Okay, thank you very much. Thank you very much, Bruno. Good afternoon to everybody that is following us from YouTube and also here from the Zoom platform. So my name is Fernando Gamarra. So I am from the Federal University of Santa Maria, from Rio Grande do Sul. And so we are going to start our technical session that its name is Navigation and Path Planning. And we will start with the first paper of this session. This session will have as first paper a paper entitled Navigation and Path Planning. And the author, excuse me, the name of the paper of this first session is CBNR Cost Map-Based Approach to Deep Reinforcement Learning, Mobile Robot Navigation. And the author is Darcy Luis Tomasi Jr. and Eduardo Todd. So will be in charge of this presentation. Darcy, are you hearing me?
Yes, I can hear you. Can you hear me?
Yes. Yes, okay. I can hear you. So good afternoon, Darcy. So would you like to present your paper, or you would like that the video that you send us could be started?
No, I would like to present.
Okay.
Okay. I will share my screen here. I hope can you see my presentation?
Yes.
Oh, yes, okay. Can I?
Sure, please.
Yes. So hello, everyone. My name is Darcy. It's a pleasure to present our research here. The name of our research is CBNAV, Cost Map-Based Approach to Deep Reinforcement Learning, Mobile Robot Navigation. This research was made by me and Professor Eduardo Totti. So, mobile robots must navigate from an aleatory point, start point, to a not previous start position. In most cases, the minimum capability to move is not enough or present an acceptable span of energy, an acceptable span of time that make this task unfeasible. Through the years, different approaches have been used to solve these tasks. The most common method is based on environment map, construction of the map. The map can be constructed online as printed by Islamic concepts, or supplied to some navigation algorithms when the map is known a priori. As said by Bugart yesterday, it's a chicken and egg problem. Despite the systems of using map, this approach still requires extensive efforts before they can work reliably on real world. And more often than it, the solution is not generalized due to the map. We can build the map online, or we can use the map only in the environment that we have the map. In nature, some animals and bugs have a different approach to navigate in the environment. For example, sniffing in lobsters, whisking in rats, and antenna in cockroaches are examples of sensors used to navigate. The information is used to both sensor measurement, adaptation, to adaptate the body to do not touch the hull, for example, here, and to propagate the information through the neural feedback control to move straight ahead, for example, here, to state from state X1 to state X2 without touch the hull. Complementary to the free collision techniques, I'm just saying free collision techniques is my name that I put in the concept. Okay, ants use pheromone-based navigation to create a safety path from starting to target position. It's a classic concept applied to ants. Now, if you cross the line, the ants cannot move. In summary, bugs do not know the environment maps, but know how to navigate through the environment without collision. Once they know the path, they can walk through the path, but a priori, they don't know the map. To replicate the navigation techniques, research based on deep reinforcement learning and recurrent neural networks are used in recent researches. The most basic approach to reward an action is to measure the angular displacement here and linear displacement between the robot base and target position. It's a very simple, just Euclidean distance and angular distance. Right? These values are applied in a gain value. How can we see here? We have alpha and beta generating the xi. Each action results in a new state, zeta, in this case. It's a name that I put, just zeta. If it's not a finalization state, robot don't touch the hull, don't match the target, this is applied to a reward function. This reward function will work like this, concerning zeta and si function in otherwise conditions. It's a basic approach to reward navigation robot in an unknown environment. In this condition here, it's a fine approach, because imagine this please look this image here. If we turn robot counterclockwise, we will reduce the angular displacement, and if we move robot forward, we will have the maximum, we will maximize the reward function. In this condition, this will work really well. But concerning these two images here, if we try to follow these equations, the basic equations to reward a neural network, we must turn the robot to clockwise and move forward. But in this condition, it's not the most promising condition to move the robot, because we have a hull. So, concerning animals and bugs, they will try to pass through the hull. in order to mitigate the behavior present here, we are proposing cost map reward functions and cost map path functions. First, CRF is a height matrix to describe where are the most promising places to navigate inside the environment. The matrix evolves with training episodes, as illustrated by pictures here. So the first episodes and the last episodes. So you can see we're not buying a map. We are buying a matrix to determine how we will training our agent. For example, concerning the last image here, the red one points are the most promising points to be. So in these points, the agent will receive more reward than in yellow points. It's just concerning CRF matrix. Okay. In order to simulate the pheromone conditions present by ants, we are creating a CPF matrix as well. This matrix will discount the reward if we pass in the same path that we already passed. For example, we can see here, when this condition is applied, we apply a discount value to reduce the reward present by the agent to each episode performed. Okay, and just to mention, we are using exactly the same function, a state function and reward function. We are just adding CRF and CPF here to discount or account or increase the reward. Our architecture is very simple. We are based in another paper. We are using a very simple network. We are using a dwelling double DBQN network, and this is our action map. Just 7 actions. Our robot in this condition just move forward and left or right, clockwise and other counterclockwise. We don't move backward. It's a very simple network. So each model I will present to you were trained during 500,000 episode steps. The policy was epsilon gradient policy concerning 400,000 episodes to match the minimal value. This is our network, and this is our agent. Okay, and batch size is 64. So we defining a baseline network, N1, and our proposal N2, concerning the equations already presented. We have created 5 environments, as you can see here. It's not a real room. We just imagine an environment and applied it to our models. It's not a real. No one is a real place. Okay. So any network were applied to any environment, generating 10 models, M1 to M10. So we trained all these models, and we try to evaluate all these models concerning these conditions. First, 10 times, 1,000 tries each time. We are evaluating only the number of times that the target position was reached. It was our option, okay? And we are trying to evaluate this hypothesis. CRF and CPF do not increase the number of reached target positions. And as usual, confidence interval is 95%. Okay. Here I have a very short video. It's our agent working environment number 1. And here we are using our best model to describe the behavior. As you can see, we have sometimes very hard conditions. In this case, our agent does not have a map. They just know where they are and where they should be. For example, here, they turn around and decide to go there. Okay. Oops, I'm sorry. Here we have the results for concerning our baseline approach. This is the values. I will not talk about the values. I will just look to you. I'll just ask you to look to the average values and standard deviation values. And this is our approach concerning CRF and CPF concepts. As you can see, we increase the average results, as you can see. And here we have a very simple t-test to measure how, if the hypothesis could be evaluated. As you can see here, only in the models trained in environment number 3 did not apply, don't appear to present the different conditions, different values to CRF and CPF, concerning CRF and CPF. All another conditions present the same, the good result for us. And here we have the summary of all the values, just to compare the p-value. And it's a very short p-value, very short p-value. So our conclusion, CBNAVE increases model generalization. Look into this graph here. We can see concerning different models, as for example in this column, we can see this model was trained concerning environment number 1, but concerning environment number 2, it's a high number of average value. But this model does not know the environment number 2. They only was applied to environment number 2 to verify how many times they will reach the part, and all the another models. These models were compared, as you can see here, and we can conclude that the CBNAVE, the CRF and CPF concepts increase the model generalization. We did not evaluate the path. It was an appointment by revisors, and we will evaluate the path in the next work. We are not evaluating the environment complexity because, for example, here we are imagining that environment number 3 are the most simple one. Looking to the conditions, we can just looking, we can say, it's the most simple, but we need to measure the complexity of the environment to affirm, it's really the most simple. So it's we are working on this start here. Once we have the metric, we will increase the number of the environments. We are working basic with 13,500 environments, and we are planning to apply all the 13,500 environments in our conditions. In different networks must be evaluated. We do not evaluate different networks. We just take the baseline network and we apply it to our study. And we are planning to deploy these results in a real robot. All the code and tests and environments and some, let me say, some tutorials to work with our approach can be found here in GitHub. Here we have some reference. Thank you. This is my contact. Thank you.
Okay. Thank you very much, Darcy, and for your presentation.
Thank you.
And we will see, we have some questions from YouTube or from Zoom, please. Do we have any question?
No questions from YouTube.
Okay, no questions. Congratulations for your paper, very nice paper, especially that part in which you take inspiration from nature, right, to develop some strategies for navigation of your agent. So you propose 2 strategies, CPF and CRF, taking inspiration from two different animals, in this case cockroach and ants. Exactly. What is the main difference between this CPF and CRF? I have seen the equations from the reward function, right? But could you explain us a little more about the difference?
Yeah, of course. Yeah. CRF, we are trying to create. It's complicated to say map, but it's not a map. It's a cost map, because we are applying, for example, if we pass through a point and we did not touch the hall, we did not touch the environment, and we pass through this point. This point we receive a reward. For example, we receive the maximum reward, 6 in my study. If I'm in this point and next action, I perform the next action, I touch the hall. So this point, it's not a good place to be, because I don't want to be near to the hall. I want to be in the middle of the halls. So in this point, I will apply a reward for example, -1. The yellow marks that I showed in the CRF matrix. Yes. So when we are training our agent, we are creating this matrix. It's not the matrix, it's a custom map matrix. But CPF, it's only to in each episode. For example, I'm performing a specific episode and I'm moving from here to another point. I will measure the points. I will create the matrix to represent the points where I already passed. And if I try to return using the same path that I already passed, I will apply a discount in the reward. We are trying to force, sorry, the English, but I will try to force the agent to move always in the direction of the target point. We decided to use CPF because during the training time concerning only CRF, our agent try to loop around just taking good rewards, because our agent creates some specific intelligence to move around in a loop, and this will increase the reward, but they will not touch the target. So we decided to create the CPF to reduce these conditions. In the video, sometimes the robot, even using CPF, they try to loop a little bit, then they decide to go to the target, because when they match the target, the reward will be bigger. Yeah? But CPF helps to reduce this behavior.
Okay. Thank you. And do you fuse after the? So you are fusing these two?
Yes, both matrix are being used in the same time. As I will not share again my presentation, but in the last line of our matrix, you can see SI plus CRF plus CPF. We are concerning exactly the same structure of the reward function, basic reward function, but we are just adding CRF and CPF to concern our conditions.
And you are always fusing these two cost maps, or there is some part of the trajectory which some has more priority?
No, we are just not, I'm sorry, Professor. We are just not using this condition, these two strategies when we touch the hole, it's a terminate condition, or when we meet the target, or sorry, I don't remember another condition is when when we define a maximum number of steps, then we will try to meet the target. So if we touch an obstacle, if we take the number of steps, and if we reach the target, and another condition, we will apply the reward function. It's a basic approach to recurrent neural networks.
Okay, and I'm just thinking about this, but would it be better? This approach, I don't know if this could be applied. This approach would be more optimized if we would design new kind of sensors, maybe, because you showed the principle that, at the beginning of your slides, that you are using bio-inspired techniques of different sensors from animals, from insects, right? So, well, thank you very much for your presentation. It was a very nice paper, and the future works that you have proposed seem very promising with relation with the path planning measure of the efficiency of the algorithms. Thank you very much. So we are going to go to the next presentation. So
it's a pleasure.
Sure. So the next presentation, its title is Addressing Lane Keeping and Intersection Using Deep Conditional Reinforcement Learning. and the authors are Victor Silva and Valdir Grassi. I don't know if Victor is here.
Yeah, I'm here. Hello, Daniel. Can you hear me?
Okay. Yes, we can hear you. Victor, would you like to make your presentation, or would you like that we could start your video?
Please start the video.
Okay, perfect.
Hello everyone, my name is Vitor. I'm a graduate student of University of São Paulo, and today I'm going to present the work addressing lane keeping intersections using conditional reinforcement learning. End-to-end in the autonomous driving domain is an approach in which the control commands of agents' actuators are mapped directly from the observations. This approach commonly relies on machine learning techniques, being deep reinforcement learning and imitation learning the two most employed. This approach has advantages such as good generalization for new scenarios, it's simple to design, and is less prone to human heuristics, since it's not hand-engineered. However, it's commonly used just for simple tasks, like lane keeping, and also it suffers from ambiguity problem, which is when the agent can't act properly just with visual information and without driver's intention. To solve this problem of ambiguity at intersections, co-developer proposed the method conditional imitation learning, in which separate modules learn specific tasks that are activated once at a time when it's necessary. Following this idea, other works were done, such as the ones of Miller, Vergara, and Osinski. Other important and recent works, related more specifically with deep reinforcement learning, use data augmentation to increase performance during training. So, in this work, we aim to design a method combining conditional learning and reinforcement learning to solve the problem of lane keeping intersections in the autonomous driving domain. Moreover, we want to control both lateral and longitudinal vehicle movements, with no need of expert demonstration and using augmentation data to improve sample efficiency and generalization. In our problem, the vehicle should navigate from an arbitrary start position to an arbitrary destiny autonomously, in a simulated urban scenario composed by T intersections on Carla simulator. The agent is expected to drive at speeds near to 20 km per hour, stay lane-centered, and turn or go straight at intersections when it's needed. It's important to note that our focus in this work is only regarding on how the agent deals with lane keeping and intersections. So crosswalks, traffic lights, gear shifting, other vehicles, and pedestrians will not be considered. To accomplish our objectives, we design our system as follows. Vehicle is equipped with a monocular camera that provides RGB segmented images. We decide to stack the last 4 frames to also get temporal information. Then, images are augmented and fed into an encoder. Besides the visual information, the vehicle also measures its speed, throttle, steering, and the angle between its heading and the direction of the path. Then, the images and measurements processed are concatenated, resulting in a latent state vector. At this point, we have the conditional part of our architecture. The route plan generates the waypoints that the car should follow and also provides a high-level command that represents the driver's intention, similar to GPS navigation assistance systems. So, according to this command, the latent state vector will be passed to one of the 3 PPO trainers. These PPO submodules are trained individually so that they can produce specific policies to perform 3 different maneuvers, which is follow lane, turn right, and turn left. Also, the policies will generate throttle and steering control. Throttle range from 0 to 1, with 0 meaning no throttle and 1 is full throttle. On the other hand, steering range from -1 to 1, with negative values representing steering to left and positive representing steering to right. In this work, we will investigate the effects of 3 image transformation: cutout color, translate, and crop. In these images, we can see examples of transformation for the same original image. The immediate reward is computed as follows: penalty of -10 if car commits an infraction, which happens when car deviates more than maximum distance from lane center, surpasses the maximum speed limit, or stops for any reason. Otherwise, agent will receive a multiplication of terms related to speed, distance from lane center, and the angle between vehicle's heading and current waypoint. Regarding to the term related to distance from lane center, the lesser the deviation, greater will be the reward. Similar to distance, the angle terms results in greater rewards when the angle difference is small. Finally, the speed term reaches its maximum when vehicle drives at speeds between the low limit and the target speed. Reward will be lesser if speed is lesser than the minimum or greater than the target speed. Our simulation are divided in 4 stages, 3 stages of training and 1 for test. In the first stage, the vehicle is set to drive around the map as indicated by the green line in the figure. Then, in the second stage, the vehicle is set to drive a more complex lap, encountering some intersections on the way. In the last training stage, the vehicle should drive random routes. All training stages are in Town 2 of Carla. During test, vehicles should drive random routes as well, but in Town 1, similar to Town 2 regarding to its structure, but with different surroundings. Some training constants that we define to count in the reward function are: minimum and maximum speed are 15 and 25 kilometers per hour. Target speed is 20 kilometers per hour. Maximum distance that the car can deviate from lane center without ending an episode of 3 meters, and maximum angle of 180 degrees. Moreover, these are the specifications of the machine that we used. In the first stage, we run our method with 3 different types of augmentation, a version of our method with no augmentation, and a VAE PPO proposed by Vergara for comparison. Videos are speeded up for convenience. For complex videos with normal speed, please refer the link on the article. The table and the graph show us that our method, with and without augmentation, have better results compared to VAE PPO. The average speed of all models are near to 18 km per hour. But the average center deviation of our method are way better than VAE PPO, which could not even complete the lap. In stage 2, we trained the best model with augmentation in stage 1 and the model with no augmentation to drive the more complex lap. The PPO with cutout augmentation present worse results during training, but much better during evaluation. As you can see on the videos, both models can stay lane-centered most part of the lap, but PPO cutout can drive with speed closer to the target. In the last training stage, we trained only the PPO cutout from stage 2 to drive random routes. We defined a maximum distance traveled of 3,000 meters as an end of an episode. This way we guarantee that the car drives many different routes with different difficulty levels. Results obtained in training and evaluation are good, mainly during evaluation, wherein the car drives with small center deviance, with average speed close to target, and drove 3,000 meters. Finally, after training process, we run our model on Town 1. The video on bottom right shows us that our agent can drive random routes in both maps with good performance. In Town 1, the vehicle actually had better results regarding to center deviance. It indicates that our method produced good generalization capability. The video on the top right presents the path followed by the car in comparison with the desired path, reinforcing the good performance. Moreover, the graph shows the variation of control inputs and speed during the path shown on the video. As you can see in green, the vehicle tries to maintain the speed close to 20 and only reduce during turns. This behavior can be noted as well in the other graph, wherein the throttle, in red, only reduces when steering moves away from zero, the blue line, to negative and positive values, which indicates turning left and right. So, in conclusion, represent an end-to-end framework based on multiple PPO trainers to address the decision-making for self-driving cars at intersection in urban scenarios on carless simulator. The results indicate that our method is a feasible approach to solve the problem of ambiguity on autonomous driving domain. We also could confirm that a good choice of image transformation can improve reinforcement learning performance and generalization capability. For future works, we want to consider other aspects such as crosswalks, traffic lights, road with multiple lanes, gear shifting, and interactions with other vehicles and pedestrians. I'd like to thank the foundations that finance this project, and thank you for your attention.
Okay, thank you very much, Vito. Do we have any questions from YouTube or from Zoom, please? Well, I would like to ask a question. Congratulations for your presentation and for your paper, Victor. This paper that you presented, you talk about a system that you have used for the problem of lane keeping, the Impala architecture that you have used. This architecture that you have used, why did you choose the Impala network? And have you at the beginning of your presentation you talked about that you stacked four images in your network. This is sequential information, right? It's sequential data. The Impala network maybe help you to process that sequential data?
Yes, that's it. I use the Impala encoder. It's just a small part of the Impala encoder, because many articles that I've read, they say that it has a good performance to extract features from images. So I decided to use an encoder based in this algorithm.
Okay, perfect. And you talk about data augmentation that improve the performance of your system, and you have used 3 methods from data augmentation. Do you remember more or less how much new images do you have to create using this technique of data augmentation for your experiments? How much new images did you have to create?
I don't remember, but at the epoch, my method used an horizon of 512 frames. So every time that we finish this horizon, I use another, I randomize the augmentation and use again, you know. I am clear.
You randomized the number of images that you have to create. Is
that's
that what you mean?
Yeah.
Okay. And you also talk that from the pictures that you have, from the figures that you have, show us that some methods of data augmentation work better than others. Right?
Yeah, because for example, if I used another transformation, for example, flip horizontally, maybe it will not learn the tasks, because you know, if I have an image indicating that I need to turn left and I flip it, the car probably will be confused, you know.
Yes.
So just using augmentation is not 100% that it will improve. We need to choose a good one.
Yeah, you have to choose that technique of data augmentation, the more adequate for your experiment. Okay, yes. Perfect. Well, I don't know if we have more questions from YouTube or from the audience in Zoom. Well, I think we don't have. Well, Victor, thank you very much for your presentation and for your paper. Now we are going to go to the next presentation. It's the title of the next presentation. It's Towards a Simple Navigation Strategy for Autonomous Inspection of Ducts and Galleries. And the authors are Guilherme Pereira, Carolina Duarte, David G. Marques, Hector Aspurua, Gustavo Pessin, and Gustavo Freitas. I don't know who is going to make the presentation. Maybe Guilherme?
I'm here.
Okay, thank you, Guilherme. Guilherme, so would you like to make the presentation from your computer, or you would prefer that we could start the video that you send us?
You can play the video, please. But okay. I just want to, in the end of the video, I would like to show 2 more slides, if possible.
Okay, it could be.
Thanks.
So playing your presentation.
Okay. Hi, my name is Guilherme, and I am a systems engineering student at Federal University of Minas Gerais. Today, I'm going to present the paper entitled Towards a Simple Navigation Strategy for Autonomous Inspection of Ducts and Galleries. First of all, we will be presenting an introduction to the problem, followed by the ducts and galleries inspection topic. Next, we describe the state machine developed for autonomous inspection, and then the systems used to implement everything. We will also present all the results obtained in simulation, and finally, the conclusions and references. The main motivation behind this work is the possibility of mitigating dangers to human operators responsible for inspecting confined environments. Among various existing risks, we can mention no ventilation, toxic gases, floods and collapse risk, venomous and poisonous animals and insects. Therefore, a feasible solution for this problem is using an autonomous robotic platform to perform these inspections, such as Espelho Robô. This robot was developed in a partnership between UFMG and ATV. It was designed to move on rough terrain and confined environments. Initially, the idea was to teleoperate the robot during inspections in natural caves. However, it was also possible to inspect dams, pipes, galleries, among other confined spaces due to its great mobility capacity. Considering that inspections in confined environments are hard tasks,
A great strategy is to implement autonomous solutions running directly on the robot hardware, without human control. The method described here is based on maze-solving algorithms and data from basic sensors, such as an IMU and a planar LiDAR. So, the main purpose here is to describe a robust, fast, and practical solution to perform inspections safely. Ducts and gallery systems are very common in the mineral industry. Normally, they are extensive corridors close to tailing dams, plants, and other industrial structures, and they are often used to transport different types of byproducts. Curves and bifurcations might make the transport of mine tailings harder, so they are mostly long and straight, as can be seen in these real-life examples.
To navigate in these sites, the idea is to assume the robot is always moving with a fixed forward velocity and a variable angular velocity, to try and keep the robot on the center line of the site it is inspecting, reduce the risk of collision or rollover. The method to control the angular velocity uses a planar LiDAR and divides its data in two sides, left and right, as can be seen in red and in blue, and then it seeks for the closest point on each side. Each point is considered as a reference for each side of the gallery or duct. The purpose is to keep the distance between the robot and each wall the same, keep it in the middle. So the distance difference is considered the position error with respect to the central position. If it equals 0, the robot is in the correct position, else a proportional angular velocity is computed, directing the robot to the center. To navigate inside ducts, the inclination is also very important. Thanks to the circular format and lack of references, the LiDAR might perceive the robot as being the center line, but it fails to detect a crescent inclination that may lead the robot to roll over. To prevent that, we use orientation data provided by an IMU. If any lateral inclination is detected, a proportional angular velocity is computed until that inclination is 0 again. The distance and orientation errors are normalized and then added. A PID controller computes an angular velocity dependent on the errors.
To navigate within the duct and gallery systems, the robot must also deal with bifurcations. In such cases, the strategy used to follow the center line, as described before, is not suitable. So, the robot needs to be able to detect a bifurcation and then change the control strategy used for navigation. Our bifurcation detection algorithm uses the distance values obtained from LiDAR and their respective angle in relation to the robot's orientation. The distance values obtained from the laser are compared with a predefined parameter. This parameter is indicated in the image by the green circle. Every group of laser beams with values greater than this parameter is considered a possible path. So the angle between these paths is calculated. If it is larger than a parameter, meaning the paths are sufficiently separated from each other, the algorithm detects a bifurcation. When identifying a bifurcation, the adopted strategy consists in commanding the robot to follow the left wall. This method allows the robot to explore ducts and galleries with a tree-like structure. This was implemented using the laser beam to the left of the robot with the smallest distance value. Then, the angular velocity is calculated so that the yaw angle is always perpendicular to this laser beam, moving with a fixed forward velocity. Therefore, the robot turns left, following the left wall whenever there is a bifurcation. The operating logic proposed for navigation can be described by this state machine. The robot generally operates in two main navigation modes: following the center line of the gallery or dealing with bifurcations until it reaches the exit and the mission ends.
In the gallery control with forward direction state, the robot tries to stay in the center line of the path. In the bifurcation control with forward direction, the robot follows the left wall. The state named gallery control in reverse direction is the same as the first one, but moving backwards. The bifurcation control in reverse direction is the same as the second one, but going backwards, with a new reference of left. Mission end state stops the robot and the inspection ends. The inspection starts unconditionally as soon as the robot turns on. The robot moves by default with the forward and reverse gallery control states until a bifurcation is detected. And then the state switches to the bifurcation control, following the left wall. If the bifurcation stops being detected, there is only one possible path to the robot, and then the code switches back to the gallery control. If the LiDAR identifies no possible path in front of the robot, a dead end is identified, and the only possibility is to return on the same way it came, but going backwards. If no obstacles are identified around the robot, it's probably an open area, and the gallery's exit is identified, ending the inspection.
Pursuing a more straightforward and modulated implementation of the state machine described before, we used a library called SMAC, which is a ROS-independent Python library to build state machines for complex robot behavior. Now, we will show the results obtained with experiments in virtual scenarios. First, there is a gallery system in a tree-like structure with 56 meters in length and 4 bifurcations. It's important to highlight that since this is a gallery with no inclination, the robot can navigate using only LiDAR data. The second scenario has 213 meters in length and is based on the real-life tailing dam duct as shown previously, and is composed of 3 main segments and 1 bifurcation. So, we were able to implement and simulate a simple autonomous navigation method for ducts and galleries with tree-like structures. We used 2 control algorithms, one for following the center line of the way, and another for following the left wall in bifurcations. The transitions between these 2 operating states were performed from the analysis of the planar laser measurements. The next steps are: run the proposed method on the real espelho robô and investigate more robust maze-solving algorithms that do not rely on precise localization or mapping, including algorithms capable of handling internal loops or more complex structures. Here are the main references of the work, the acknowledgements, and feel free to make questions or suggestions. Thanks.
Okay, thank you very much for your presentation, Guilherme. You said that you have 2 more slides that you would like to present.
Yes. Can I share my screen?
Yes, please.
Can you see my screen?
Yes.
Just some images about ducts and galleries inspection sites. Above we can see the galleries systems, and below we can see the ducts systems. And the last image, we can justify the use of the IMU to prevent rollovers of the robot. And another image. This is a simulation overview of the results shown in the presentation. This is a reconstructed map of the reconstructed in Coppelia-Sin. And here we can see the inspection start point, the robot entering the duct system. He navigates following the center line of the duct. He deals with bifurcations following the left wall and come back in dead ends. That's it. feel free to make questions or suggestions.
Okay. Thank you very much, Guilherme. Now, let's see, we have some question from YouTube or from the Zoom audience.
Hi, Fernando. I have a question.
Yes, please.
Guilherme, thank you very much for your presentation. Very nice work.
Thanks.
I have a simple question, actually. Something that is not clear to me is how do you prevent that your robot enter in a loop? I mean, it goes until the end of the gallery, then it goes back, then it's find it's a less bifurcation in which it's visited, and then it takes the other direction. And when it comes back, how do you prevent that he took the direction that he already took before?
Yes, our algorithm works for 3 light structures. Following always the left, we can inspect all the 3 light structures. If there are internal loops or more complex structures, this method will not work to inspect all the system.
Thank you, Guilherme. I look forward to see this algorithm that you have implemented on a real robot. Thank you.
Thank you.
Thank you, Bruno. Thank you for your presentation, Guilherme, and congratulations for your work. Very nice work. It makes me remember a little bit the robots that the principle that Rodney Brooks used in a famous robot is used to make his robots using inspiring insects and using a very reactive architecture. Something like a little bit, it makes me resemble something as the one that you have designed. So you have introduced two strategies. One for one strategy, you follow the center line of the corridor, and the other, when you have bifurcations, you have to the left, right? So you were talking about there is a threshold, a parameter that when you are in a bifurcation that you choose to go to the left to the corridor. This parameter or this threshold is related to what? I don't know if you remember.
This threshold is related to bifurcation detection. So there are 2 main thresholds used for bifurcation detection. One is the threshold of distance of the laser beams, because the method uses the values of distance of lasers, and another is to a threshold related to the angle between 2 paths. So the values greater than one parameter are the group of lasers greater than a parameter is considered a path. So then the paths are compared, the angle between these paths are compared, and if it's greater than the parameter, we detect bifurcation.
Okay, thank you. And thinking in the practical application that you are planning, right? You already have for the pictures that you have shown us, you already have the robot constructed, and you have the algorithm that it's ready. You have shown us in the simulations that it works. So just in the practical application, like this robot is going to work in pipelines, for example. I don't know if your group, I don't know if this is part of your work, have considered, for example, when you go in pipelines, you are going to have maybe a lot of water or something like that. Have you, your group maybe have think to contour this problem, to avoid this problem? Have you thinking some strategy, or maybe there is other kind of group that works just the hardware part?
Yes, it's other type of work, but the robot is waterproof. The robot is prepared for HOF environments, and it was initially built for inspection caves and scenarios and HOF scenarios, but now for the needs, it's being used for inspecting galleries, ducts, and another systems like this.
Okay. As Bruno said, we are going to be expecting for the experiments with the real robot. That is, I think it's going to give a very nice work. Well, thank you very much, Guilherme, for your presentation.
Thank you.
Thank you. With your presentation, we are closing this technical session about navigation and path planning. Just remembering that tonight at 19 hours, we are going to have the virtual cocktail. So I'm passing the word to Bruno, maybe if he wants to add something, or we close here.
Thank you very much, Daniel, for chairing the session for us. Just reiterating the invite to everyone. We will be live right here in this channel on Zoom, live streaming to YouTube as well, starting from 7 p.m. or 19 o'clock. There will be a cultural show that we all hope that you will enjoy. And saying again, if you want to meet and greet, just use our Discord channels, our Discord server. Oh, sorry, my motorcycle. Just use our Discord server, and in there you can talk to each other. We can have a conversation. We can have maybe a virtual drinking or something like this. Okay. So we'll see you at 7 o'clock. Thank you very much for being with us in day 2 of LARS. See you at 7 o'clock in the virtual cocktail. Thank you.